So the second type of function that's going to be important to us when talking about relationships between sets is what's called an onto or a surjective function. And you can read the definition here, right? A function is onto if and only if for every y in the set y. So now we're looking at values from the codomain. There exists an x from the domain such that y equals f of x. And I've got the formal version down here, but what this is saying is now every value in the codomain must have a corresponding x value. Remember, we talked previously, we saw some examples where there were values in the codomain that didn't have a matching domain value. Right? We specifically talked about that being okay for the codomain, where it wasn't okay for the domain. Well, these onto functions add that additional restriction. Now, there has to be a match both ways. Right, so not only I have the logical version here, and what I really want you to focus on as well here is this second line. That's the negation. So this is what I need to look at to see if a function is not onto. For a function to be not onto, there has to be a number, all it takes is one, a number in the codomain such that there is no x in the domain that maps to that value. Okay, a lot of technicalities there, right? Let's look at some examples. I have these two functions again here, right? We've been using these throughout this section. And I want to talk about, are these onto or not? Well, remember, for something to be onto, I'm focusing on the codomain, and I'm saying, does every element in that set get matched up with something on the domain side? All right, so on this first one here, that is not the case, right? This value doesn't go anywhere back in the domain. So this function, it is a function to be clear, this function on the left is not onto, where this function on the right is. Right? Again, focusing on the codomain side here, every value has an arrow coming into it, right? And that's what I'm looking for a function to be onto. All right, so how can we do this with a more generalized function, right? Something from an infinite set to another one, right? Something where we can't just kind of look at individual values. Well, what I need to do here is I'm going to do this in a constructive way, right? I'm going to say let y be an element of R. Specifically, that's this second R here, right? Let y be an element of the codomain. What I need to do is I need to find an x value such that f of x is equal to y. And it's hopefully a little bit clear how you do this. If you take this formula here, and if we rewrite this y equals 3x plus 2, and you solve this for x, we get x equals y minus 2 divided by 3. That's my x value. All right, so let y be an element of R, then f of y minus 2 over 3 is equal to, and I'll actually work it out here. Let's substitute it into my function formula there. 3 times y minus 2 over 3 plus 2. This is y minus 2 plus 2, which is y. And that's what I needed to do. This x value gets mapped to that arbitrary y value that I've chosen. Okay, so what did I show? Therefore, every y in the codomain has a corresponding x value in the domain. Specifically, x is equal to y minus 2 divided by 3. So this function is onto. Okay, so how about a function that is not onto? Well, you know this is practically identical right to the last one. I just tweaked one thing. I changed the domain. Right, so the domain is now not the real numbers anymore. It's just the integers, and my formula doesn't work anymore. Right? If I pick y to be, let's say 1/2. All right. Well, try to find the x value. Right? 1/2 equals 3x plus 2. So we'll subtract 2 from both sides. Minus 3/2 equals 3x. Divide both sides by 3. X is negative 1/2. And that, unfortunately, is not an integer. And that's the only value that could possibly have worked. So therefore, this function is not onto. You notice how I did use the negation there, right? I needed to show that there exists an element in the codomain that does not have a value in the domain that maps to it. Okay, so that's how we show one way to show, right? A quick way to show that a function is not onto. You find a counterexample. So I've got one more definition here, and I'm not going to really belabor this one because it's pretty straightforward. A function is a bijection or a one-to-one correspondence if and only if it is both one-to-one and onto. Right? It meets both of the new definitions that we talked about, one in this lecture and one in the last one. Okay, so this is going to be the end of our explicit discussion of functions. We've got all the concepts that we need now to move on and start doing the things that we really want to do from a discrete math and a set theory perspective. In the next lecture, we're going to look at a couple of specific examples of functions, right? Functions that come up in different practical settings, and then from there we'll move back into set theory and start talking about how to compare the sizes of sets.